everyone. In this video I'm going to show you how to build a Mealy and Moore machine that detects the sequence 101. So what is required is that we have a sequence, okay, that is fed to a machine, okay, and this sequence is called X, so it's a bunch of bits, 0, 1, 1, 0, 1, 0, 1, 1, and so on and so forth. And the output is Z, okay, and we want this Z to be 0, to be 1 if the sequence 101 has occurred, okay, and we want it to be a 0 otherwise, okay. So that is what is required. This is the input, a sequence of bits that comes one after the other. The bits come one after the other, and for each corresponding bit, we have an output bit. If the previous 3 bits were 101, we want the output to be 1 when this last bit comes. Okay, so we want it to be 1, we want it to be a 0. So when we receive a 1, we want the output Z to be a 0, then a 0, then here we want a 1. Okay, so let me first explain how to do the Moore machine and then proceed with the Mealy. Okay, the Moore machine. Start with an initial state which is we call a 0. This is the reset state. Okay, whenever you power on the machine, you assume that the system is in this state, and definitely you expect that the output in that state is going to be 0. Okay, and so this is the Moore machine. Okay, so the output is going to be a 0. Whenever you power on the machine, you expect that the machine will power on at this state. Okay, so what happens if you receive a 0, and what happens if you receive a 1? What happens if X was 0, so this is X, because at this particular state, once you power on the machine, you expect that the machine will receive either a 0 or is going to receive a 1. You do not know, so you need to take both cases into consideration. If you receive a 0, do you expect that you are going, is it a part of the sequence? Is it a part of the sequence that we're looking for? Actually it is not, we're waiting for a 1. So this is why you will keep looping back to the state as 0, because you did not receive the 1 that you're looking for. Okay, so what happens if you receive a 1? Of course, if you receive a 1, you need to go to a second state, and let's assume it's called S1. Okay, so in our definition table, this is the definition, state, definition, table. We have state S0, which represents initial reset state. Okay, what about S1? So initial reset state means that no sequence was detected yet. No parts of the sequence. Alright. What about S1? S1 here represents that I received 1. Last bit received is 1. Okay? What do you expect the output to be? Well, we want the Z to be 0. When we receive a 1, when we receive the first 1, we want the Z to be 0. That's why I'm going to put 0. Okay? Later on, when we look at state S1, I could either receive a 0 or I could receive a 1. Okay? So what happens if I receive a 0? Does this 0 represent a part of the sequence that I'm looking for? What is the sequence that I'm looking for? I'm looking for 1, 0, 1. Okay? So again, since I'm looking for 1, 0, 1, and I have, so this is the X, and this is the Z, Okay? So this 0 represents this 0. Why? Because so far I have received 1, 0. So far, let's look, so far I have, when I'm at state S1, okay, when the machine is at state S1, I have received 1, 0 so far. With this 0, I have received 1, 0 so far. State S1 represents that I have received a 1. And this arrow represents that I have received a 0, which means that I have received 1, 0 so far. Does this 2 bits, do these 2 bits represent a part of the sequence that I'm looking for? Yes, in fact they do. And that's why I need to go to another state S2. Okay? And the output is still going to be 0. Okay? However, if I receive a 1, does this represent a sequence from, so what have I received so far? 1, 1. With this one represents that I have received so far 1, 1. This sequence does not represent a part of the sequence that I'm looking for. Okay? So, does this mean that we need to go back to the reset state or not? Actually, we do not. We need to go back to this state S1. Why? Because yes, this is not a part of the sequence. However, the last bit is a part of the sequence, which is the 1. So if for instance, the next 2 clock cycles, I receive the 1, 0, then I will make use of this one. Yes, I'll not make use of the one previously received, but I'll make use of this one. And this is why I need to loop back to state S1. Okay? Why do I need to loop back to state S1? Because S1 represents that last bit is 1. Okay? So, finished these 2. So let's proceed with S2. S2, I need to study the case if I receive a 0 and if I receive a 1. If I receive a 0, what happens if I receive a 0? Well, a 0 is followed by a 0, is preceded by a 0, and then preceded by, and previously preceded by 1. So far I have 1, 0, 0. Is this a part of the sequence that I'm looking for? It is not. So I cannot assume that it is a sequence. I cannot output a 1 so far. So let's look at these 2. Are these 2 a part of the sequence that I'm looking for? No, it is not. Why? Because I'm looking for 1, 0, 1. So neither the 0, 0 is a part of the sequence, nor the 1, 0, 0 is a part of the sequence. And this is why I need to proceed with this 0. Is this 0 a part of the sequence that I'm looking for? I'm looking for 1, 0, 1. It is not. So this is why this arrow is going to loop back to the initial state. Receiving 2 zeros in sequence, okay, even if whether they're preceded with a 1 or preceded with whatever, I do not care. This is not, none of them is a part of the sequence that I'm looking for, which is 1, 0, 1. And that's why I need to go back to the reset state. Okay? Let's move on to the 1. Okay? If I receive a 1, so far I have 1, 0, 1. Okay? 1, 0, and then receive a 1. Is this a part of the sequence that I'm looking for? Yes, it is. And that's why I have to build a third state, and the output in that case is 1. Okay? So what does this state represent? This represents that if you received a 1 after being at state S2, then this one should trigger the output such that it outputs a 1. Okay, and this is why I've written down this state name inside the bubble and written the output associated with this state. Okay? So, again, what does S2 represent? Represents last 2 bits are 1, 0. 1, then 0. Okay? S3 represents last 2 bits, last 3 bits are 1, 0, 1. Okay? So, and that's why the output associated with the S0, that is the output Z, is going to be 0, associated with S0, and then 0 associated with S1, and then a 1, no, that's a 0, associated with S2, and then 1. So S0 is 0, S1 is 0, S2 is 0, and S3 is a 1. Okay? So let's move forward with the S3. Shall I stop at S3? No, I actually need to find out what happens if I received a 0 and what happens if I received a 1. Although this is the winning state, this is the last state, the final state that I need to study. However, I need to study because when the machine reaches this state, when the machine reaches 1, 0, when the machine receives 1, 0, 1, and becomes at state S3, you need to tell it what happens if I receive the fourth bit becomes a 0, and what happens if I received the fourth bit as a 1. If the fourth bit was a 0, then 0, 1, 0. So far I have 0, 1, 0, and then proceeded with a 1. So far 1, 0, 1, 0. 1, 0, 1, 0. Is this 1, 0, 1, 0 a part of the sequence? No, it is not a part of the sequence. So I cannot assume, I cannot neglect it. So let's look at the 0, 1, 0. Is the 0, 1, 0 a part of the sequence? No, it is not. None of them is 0, 1, 0. None of them is a part of the sequence that I'm looking for. Okay? So let's look at 1, 0. Is 1, 0 a part of the sequence that I'm looking for? Yes, 1, 0 is a part of the sequence that I'm looking for. Okay? And this is why I need to go to, where is 1, 0? This is 1, 0. Okay? So I need to go to state S2. Alright? Again, what does this arrow represent? This arrow represents that if I'm at state S3 and received a 0, according to the sequence that I have so far, which is 1, 0, 1, 0, I have a part of it is a sequence. The last 2 bits of that sequence is a part of the sequence that I'm looking for. So why do I need to do this? Just in case I receive another 1, I have to output a 1. Okay, if I receive another 1, I have to output a 1, because 1, 0, 1 is a part of the sequence that I'm looking for. Okay? And when you're at S2 and receive a 1, you are going to go to S3 and thus output a 1. Okay? When I receive another 1, what do I have so far? I have 1, 0, 1, 1, 1, 0, 1, 1. Okay? This is not a part of the sequence. This is not a part of the sequence. This is not a part of the sequence, but this is a part of the sequence, which is the 1. And that's why I need to go to state S1. Why did I go to state S1? Because the state S1 represents last bit received is 1. Okay? Alright? So, let's do so what do we learn from this problem? We learned that in order for us to build this state diagram, you need to begin with an initial reset state, and you also need to consider all the cases, 0 and 1, 0, 1, and try to make use of the states that you have so far. This 0 goes back to the reset state, and this 1, you need to build another state if you cannot make use of the previous states. Okay? So you have to consider all the possible cases, and write down the cases that you have so far. For example, at state S2, I have 1, 0, 0. Or I have 1, 0, 1. So write it down, 1, 0, 0 and 1, 0, 1. Write down this sequence and find out whether this is a part of the sequence that you're looking for or it is not. Okay? So make use of this scratch paper so that it helps you decide if you need to carry out another state or the states that you have are sufficient. If you need to write down to create another state or not. Okay? Let's continue from here. Yes, we have a state diagram, but we do not have a machine. We're required to build a machine. And we're required to build a machine using the Moore steps, which means that we need to follow these steps. Okay? So let's build the machine. Okay? The way that I'm going to build the machine is as follows. Okay? I'm going to first create what is called state transition diagram. Transition diagram. Okay? So that's the second step. So the first step is the state transition table. Sorry. Again. State transition. Transition diagram is the first step. Okay? And then state transition table is the second step. So that's the state transition diagram. And then the state transition table, then the K-maps. Okay, and fourth, you need to write down the equations from the K-maps. And then the fifth step is to build the machine. Okay? The first step is to draw the circuit using these equations. Once you have equations, you can build the circuit. Okay? So let's do the state transition table, which is step number 2. State transition table consists of the input, x, okay, and then present state, next state, and then the output. Okay? So here in the present state, what do I write down? I write down S0, S1, S2, S3. These are the possible states. Okay? But I need to consider the possible states when the input x is 0, and I need to consider them when the input is 1 as well. So what happens when the input is 0, and what happens when to these states when the input is 0, and what happens to the same states when the input is 1. Okay? And I'm going to write down here the binary assignment. Okay? I'm going to write down here the binary assignment, but I'm going to postpone it till after we finish the state transition table. Okay? So, S0, since this is a Moore, S0 is associated with output equals 0. S1 output equals 0. S2 output equals 0. S3 output equals 1. Again, 0, 0, 0, 1. Okay? So that's the output Z. Okay? That is the output Z. Okay, after filling in the output Z, what do we need to fill in? We need to fill in the next state. How shall I fill in the next state? The next state actually comes from the state diagram. Okay? So, we have S0 and an input of 0. S0 and an input of 0. What's the next state? The next state is S0. S1 and an input of 0. S1 and an input of 0. The next state is S2. Okay? S2 and an input of 0. S2 and an input of 0. This goes back to S0. So I write down here S0. Okay? S3 and an input of 0. S3 and an input of 0. Go back to S2. Okay? S0 and an input of 1. S0 and an input of 1. Go to S1. S1 and an input of 1. That's loop back to S1. Okay? S2 and an input of 1. That's S2. Input of 1 goes to S3. S3 and an input of 1 goes to S1. Okay? So, to the binary assignments. What do we do in the binary assignments? We need to represent these states with, what do we need to? We need to present these states with binary. So what I'm going to do is that I'm going to assign here a binary 0, 0 to state S0, binary 0, 1 to state S1, and then here 1, 0, and then 1, 1. Okay? These are arbitrarily chosen. I chose it to be S0, so it's assigned to 0, 0, and then 0, 1, 1, 0, and 1, 1. Okay? So S0 is 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 1. Okay? And then this is 0, 0, this is 1, 0, this is 0, 0, S2 is 1, 0, S1 is 0, 1, okay? S1 is 0, 1, S3 is 1, 1, and then S1 is 0, 1. Once you have this state transition table, then you're ready to go to do the K-maps. You do not really need this state diagram anymore. So let's proceed with the K-maps. What are the K-maps? How many K-maps do we need? 1, 2, and 3. Okay? So, let's first name them. This is Q1, and this is Q0. Again, let me rename them again. These are the states. We have here Q0, and this is Q1. Okay? So this column represents Q1 plus, and this is Q0 plus. Okay? So this column represents Q1 plus, and this column represents Q0 plus. So the steps of the K-maps are pretty standard. Let's do the K-map for the D1. Okay? I'm assuming that these flip-flops are all D flip-flops. That will facilitate the process a lot. Okay? So let's do the K-map for D1, which is for the column which is equal to Q1 plus. Okay. How do I do the K-map for Q1 plus? First of all, I need to decide how many variables do we have. We have number of variables. Let me write it in a note here. Number of variables equal number of inputs plus number of flip-flops, which is equal to the number of states. I'm sorry, which is equal to the number of variables that you have. We here have 2. We have 2 variables because Q1 and Q0. Okay? We have 2 assignments. 0 and 0, 0, 1, 1, 0, 1, 1. So we have 2 bits, a pair of bits. So that's why we have number of flip-flops is 2. Okay? Plus the number of inputs, which is x. So we have only 1. 1 input, which is x. Okay? So that's 1 plus 2 equals 3. So it's a 3-variable K-map. 3-variable K-map. Alright? What's the first one? X. Then Q1, Q0. Okay? So how are we going to fill it in? This is 0, this is 1, this is 0, 0, 0, 1, 1, 1, 1, 0. Okay? So, this is going to be 0, 1, 2, and then 3, 4, 5, 6, and then 7. 0, 1, 2, 3, 4, 5, 6, and 7. Right? So the first row, let's fill in the Q1. You need to repeat, let's repeat this again for the D2, because it's going to be exactly the same. I'm sorry, for the D0. Because it's going to be exactly the same. Here X, Q1, Q0. 0, 0, 0, 1, 1, 1, 1, 0. 0 and 1. Okay? And then 0, 1, 2, and 3. 4, 5, 6, and 7. Right? So, let's bring this column and fill it in inside the Q1 table, the Q1 K-map. So it's 0, 1, 0, 1. 0, 1, 0, 1. Okay? Because it says 0, 1, 2, and 3. So 0, 1, 0, 1. Okay? That's the second, that's the 0th row, the first row, the second row, and then the third row. 4th, 5th, 6th, and 7th. Okay, so we have 0, 1, 0, 1, 0, 0, 1, 0. So 0, 0, 1, sorry, 1, and then 0. Okay, and I'm going to remove these so that they do not interfere with the numbers that we have. Okay, let's fill in the D. 0, 0, 0, 0. D0 is 0, 0, 0, 0. 1, 1, 1, 1. 1, 1, 1, 1. Of course, 1 and 1. Right? Okay, let's solve this K-map. Right? Which means that it's D1 equals, these two are common, so it is a Q0. And then X bar. What about D0? D0 equals X. Because, right? So these are the two equations that we have. Am I done? Not yet. I need to have an equation for the output Z. Remember this, whenever you have a Moore machine, do not look at the state transition table in order to do a K-map for the Z. Look, it suffices to look at the state definition table. So I'm going to write down here the state definition table, and it is going to be a two input K-map, 1 and 2, right? So that is for the Z, a two input K-map, Q1 and Q0. This is 0, 1, 0, 1. 0, 0, 0. Okay, so what happens if I have a 0, 0? The output is 0. 0, 1, the output is 0. So 0, 1, the output is 0. 1, 0, 1, 0, the output is 0. And then 1, 1, I have an output of 1. So the output Z equals Q1, Q0. Right now, I have equations that I'm able to solve to do the circuit. Right? So let's build the circuit. How do you build in the circuit? So these are the three equations. 1, 2, and 3. Okay? First of all, the first step to build the circuit, you need to draw the flip-flops. That's the first step. Draw the clocks of the flip-flops and connect them together to a master clock. And we are assuming that they are D flip-flops. So this is D1 and this is D0. This is Q0 and this is Q1. Alright? So, what is feeding D1? D1 is fed by Q0 multiplied by X bar. So it's an AND gate, has an input of X bar, and sometimes some people like to write it this way. That's an X. Okay, so that's X bar. And then a Q0. And instead of doing that mess, I'm going to write down here Q0. Okay? And what about the D0? The D0 is fed with X. So that's the D0. What about the Z? So we finished the D1, D0, and then the Z. The Z is AND gate between the Q1 and the Q0. Right? And that's an AND gate, which is the output Z. And this becomes the circuit. Right? This becomes the circuit that implements a 1-0-1 sequence detector. So whenever you feed here a 1-0-1, you end up having an output 1 at the third bit. Okay? So let's quickly do the Mealy machine and let you know what the procedure for the Mealy machine is. Okay? Mealy machine. The Mealy machine. As usual, start with a reset state. But do not write down the output inside the state. Okay? So that's the reset. Okay? Do not write down the output inside the state. Okay? What happens if I get a 0? And what happens if I get a 1? If I receive a 0, then the output is expected to be 0. So that's why you need to write it down on the arrow. That's the difference between a Mealy machine and a Moore machine, is that in the Moore machine the output was inside the bubble, was inside the state. However, for the Mealy machine, the output is outside the bubble. The output is on the arrow. Right? So go to state as 0. If I receive a 1, still this 1 is a part of the sequence, but the output should be still a 0. Okay? And I go to state S1. Again, do not write down any outputs inside the state. Right? So, 1, 0. Totally, right now I have, so S0 is initial. S1 is received 1 so far. So I have received 1, a logic 1 so far. The last bit was 1, right? If I receive a 0 and if I receive a 1. If I receive a 0, it is a part of the sequence. However, I should not let the output be a 1 yet. And that's why I've written down here a 0. Okay? Where should this arrow go? It should go back. It should go to a third state, which is called S2. Alright? And what happens if I receive a 1? If I receive a 1, then so far I have 1, 1. Is this a part of the sequence? It is not a part of the sequence that I'm looking for. Is this a part of the sequence? Yes, the 1 is a part of the sequence that I'm looking for. So I need to look back to state S0, S1. And this becomes a 1, becomes a 0. Right? Because I do not have any, I should not output as a 1 yet. Right? State S2, if I receive a 0 and if I receive a 1. If I receive a 0, I know for sure that this is not a part of the sequence. So I should not output a 0. I should not output a 1. Right? This is an output of 0. But where should I go to 1, 1, 1, 0, 0? This is not a part of the sequence. This is not a part of the sequence. This is not a part of the sequence. So I go to the initial state. 1, so 1, 0, 1. I have to output a 1. But where should I go to? I do not really have to go back to, I do not really have to create a third state S3. Why? Because if I really create a third state, that's really a redundant state. Previously, I had an arrow, I had an output in every state, so I cannot do except create a new third, fourth state, right? Let me repeat this again. So, let's have a look at 1, 1. I'm assuming I'm going to tell you that state S2, when it receives the 1, I will output a 1, and so far I have 1, 0, 1. So 1, 0, 1 is not a part of the sequence, 0, 1 is not a part of the sequence, 1, 0, 1 totally is a part of the sequence, but the 1 itself is also a part of the sequence, in case something else, some sequence that match the 1, 0, 1 comes in the future. So again, 1, 0, 1 is not. 1, 0, 1 is the part of the sequence, that's why I output the 1. However, 0, 1 is not a part of the sequence. Okay, so I should ignore it. But the 1 is a part of the sequence, and that's why I went to state S1. Okay? In the Moore machine, previously I had in the state S1, I had an output of 0. And that's why I was not able in the Moore machine to go back to state S1. However, in the Mealy machine, I can go back to state S1 because I know that S1 does not represent an output of 0. It represents an output, it represents receiving the last one, and it does not represent an output of 0. Okay? So, and that's why I can output here a 1. But in the Mealy machine, there was an output of 0, and that's why I had to create a new state S3 with an output of 1. Right? So that's the difference, and that's why the number of states is reduced, okay, from the Mealy compared to the Moore. Okay? Let's map this to the transition table. X, present state, next state, and then the output, Z. Okay? 0, 0, 0, 0, 1, 1, 1, 1, S0, S1, S2, S3. And I'm going to let you know why I've written down S3 here, S0, S1, S2, and S3. Okay? I'm going to let you know why I have written down S3, although I do not use it here. Okay? So, as opposed to the Moore machine, whenever I look at the transition table, I need to look at the output and fill in the output first. Okay? Let me define these first. This receive 1, 0 so far, and that's it. And S3 is don't care. Why is S3 a don't care? Because we have, when we do the binary assignment, we have 0, 0, 0, 1, 1, 0, and we need to assign 1, 1 to something. So that's why I need to assign it to S3. So I need to write down, take into consideration the S3 in the transition table. Okay? So, S0, I receive a 0, and I have an output of 0, and the next state is S0. Okay? S1, and I receive a 1. I go to state S0 and S1 and receive a 0, and I go to state S2, and the output is 0. Okay? So right now I filled in the output column along with filling in the next state, as opposed to the Moore machine where this was not the case. I filled in the output in the Moore machine based on this initial table, based on this state definition table. Okay? So the state definition table in the Mealy machine does not have any binary assignment, any outputs associated with the states, because I do not have any outputs associated with the states. Okay? So S2 receive a 0, S2 receive a 0, go to S0, and output of 0. S3 receive a 0, there is no S3, then don't care. Okay? I do not care what's going on here. S0 receive a 1, go to S1, and output of 0. S1 receive a 1, S1 receive a 1, go back to state S1, output of 0. S2 receive a 1, output is 1, so S2 receive a 1, then go to state S1 and receive an output of 1, and then that's a don't care, that's a don't care. Okay, and of course the output here is don't care, because I do not care what the output is when I'm at state S3. Assuming if the machine went to state S3 and received the 0, then I do not care what the output is, because I guarantee that 100% the machine will not go to S3, because I did not really use S3. The transitions are going to be between S0, S1, and S2. I'm not going to go to state S3, and that's why I do not care what the output is. Right? Binary assignments, 0, 0, 0, 1. 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 1. This is 0, 0, this is 1, 0, this is 0, 0, that's a don't care, alright? I do not care which state to go to. That's 0, 0, no, that's a 0, 1, 0, 1, 0, 1, and then don't care. Okay? To the state, to the K-maps. K-maps. This is Q1, Q0, Q1 plus, Q0 plus, as before. Okay? This is X, Q1, Q0, 0, 0, 0, 1, 1, 1, 1, 0, 0, and 1. And this is for D1. Okay? 0, 1, 0, don't care. 0, 1, 0, don't care. 0, 0, 0, don't care. 0, 0, 0, don't care. For the D0, 0, 1, 0, 0, 0, 0, 0, 1, 1, 1, 1, 0. Q1, Q0, and that's the X. 0, 0, 0, don't care. 0, 0, 0, don't care. 1, 1, 1, don't care. 1, 1, 1, don't care. What's the value of D1 from this diagram? D1 equals X bar Q0. Right? X bar and Q0. D0 equals X. What about the output Z? For this particular case, for the Mealy machine, you cannot depend on the state definition table in order for you to build the K-map for the output Z. You have to depend on the state transition table. Okay? Again, Q1, Q0, then X, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, okay? 0, 0, 0, don't care. 0, 0, 0, don't, oops, 0, don't care. 0, 0, 1, don't care. 0, 0, 1, don't care. So I'm going to circle it this way, and the Z is going to be equal to X multiplied by Q1. Right? Okay? Final thing is the circuit. 2 flip-flops. Okay? D1, D0, Q1, Q0. Okay? What is feeding the D1? X bar Q0. X bar Q0. Alright? What is feeding D0? X. So you put here an X. What is feeding the output Z? AND gate between the X and the Q1. And this is the output Z. Okay? Right? And this becomes the output Z. It is very highly advisable to connect a D flip-flop here that has a clock connected to this clock. Why? This is called the sync flip-flop, the synchronization flip-flop. Okay? So that, because as you can see, that this output Z is a function in the input. So if the input changes within the clock cycle, you expect that the output is going to change, which is highly undesirable. And that's why you want to synchronize the output with the clock. So that's why you pass the output Z with the clock, and this becomes your real final output. Okay? So this becomes, and if you found the Mealy machine is not working, then most likely you have forgotten the synchronization flip-flop. Okay? I hope this helps, and please let me know if you have any questions.